Electromagnetic waves, electromagnetic spectrum, and light. So you may not know this, but you have lots of experience with electromagnetic radiation or electromagnetic waves. And so if you have ever been around a radio tower or listened to a radio or had an X-ray or seen visible light, you see color. If you've ever been in the sun or got a sunburn, or if you've microwaved food, you have used and been exposed to electromagnetic radiation. So what is an electromagnetic wave? You have your notes. We are right here. You should highlight this, and you can pause the video to copy this down. An electromagnetic wave is a transverse wave. So those are the ones that go up and down or back and forth. Not like a longitudinal back and forth, but like, it involves a transfer of magnetic and electrical energy. And here is a model of that, which I will let you copy down later, so you don't have to now. There are three special features that I think you should know about electromagnetic or EM waves. They are transverse waves made of two components, magnetic and electric. And so together that makes electromagnetic wave. Yeah. And then two, these do not need a medium. They can go through the vacuum of space. And so that is why we can see sunlight, because those light waves travel through nothing, so emptiness of space. The third thing is that they all have the same speed. And so we talked about sound and how sound can travel different through different mediums. Light and electromagnetic waves always travel the same speed, 299,792,458 meters per second. So it's very fast. The model that I would like you guys to copy, so in your notes it says to make a model, draw a model, is this right here. And so what you can do is draw a line on your paper and then draw one transverse wave that goes up and down. Right? And then and you should color this red and label it electric field. And then the blue is the magnetic field. Okay? And so you can do that now. When you're done, you move on. And the bottom of our page of notes talks about the electromagnetic spectrum. And this is just the range of all types of electromagnetic waves and radiation. And so just like if I were to talk about height, in our classroom, student height. Okay, we don't just have like students who are 4 feet tall and then 5 feet tall and then 6 feet tall. We have a variety. There's a range, right? From the shortest student to the tallest student, we have students that are all in between. That would be called a spectrum or a range. And so the electromagnetic spectrum is from the longest wavelength electromagnetic waves, which are radio waves, all the way through gamma rays. And we're going to talk about each of those. And so on your notes, you can copy this definition right here, the range of all types of electromagnetic radiation. You can pause and do that. And then the only thing I want you to do here, I want you to see that we have, this looks like what you see in your book. And right here, you should write visible spectrum, and you can even color it. And if you noticed, the farthest left is red. And if you notice right here, this is infrared, which infra means before. So before red is infrared. Then we have red, orange, yellow, green, blue, indigo, violet. And then ultra means after violet. And so I think that's a neat way to remember that our rainbow, our visible spectrum, is right in the middle. And we'll talk about that a lot later. So from the lowest energy, which I put on the back of your page, from lowest energy to highest energy. And so all you need to do right here is just draw like an arrow pointing down. And so energy increases. Okay, so energy is increasing from up here to down here. So the lowest energy waves are radio waves. The microwaves have more energy. Infrared have more energy. Visible light has more energy. And so it's just increasing energy. So X-rays have more energy than infrared. If we look at our visible spectrum, red has less energy than purple because purple is further along in our spectrum. Okay, I can explain that more if you need some help. Okay, so the radio waves have the lowest energy, longest wavelength, and the lowest frequency. So energy and frequency will be the same. So if it has low frequency, remember that's like up and down, it has low energy. What are some examples or uses? Send radio signals. They're used for radio phones. Some people have those. And there's a lot more to this, but I'm just giving you kind of the basics. All right. So actually, what I did is I just drew like a very long wavelength wave here. Okay. Next is our microwaves. We love our microwaves. We can cook our food very quickly. And so what they are is it's a second least energy. So they use more energy than radio waves, but not as much as anything else. They are used to cook food. They're used to send cell phone signals. And so if you have a cell phone or even remote control in your house and you're pushing buttons, that's using some form of radio or microwave or somewhere in between. Radar, radio detection and ranging to calculate speed. So like cops will use that when they're trying to find your speed. So these are all examples here. And they have slightly shorter wavelengths. So if you can start to see this from here to here, it's like the whole box, and here it's like not quite the whole box. And so they have shorter wavelengths than radio waves, but they're longer than others. Next is infrared rays. And so if you've ever seen like a thermal picture that's using infrared, it's heat. So for examples or uses, you can write heat in your box. Heat lamps use them. So anybody that has chickens that you've gotten and you put a little heat lamp on them, that's infrared radiation to heat it and cook it. Not cook, hopefully. And then if you have food that's keeping warm, it's invisible light. So it's around us, it's happening, but we can't see it. Some animals actually can see infrared, which is neat. And it is right before the visible spectrum. So remember, infrared, visible light, rainbow, and so here I'm just having, and if yours doesn't look just like this, it's okay. I just want you to start to see that the wavelengths are getting smaller. There's less space in between the crest of each wave. Oh, that's a nice little infrared picture of a dog. Okay. The visible light, this is, I think, my favorite part of it, just because I like to be able to see color. So white light can split. If it goes into a glass prism, it splits. We'll talk about that more later. And it creates the visible spectrum. So red, orange, yellow, green, blue, indigo, violet. You do need to know the spectrum. I think that's something that you've probably learned in art class like a long time ago. And so if it helps you remember, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And here, okay, I'm getting smaller wavelengths. There's less space in between my waves. Red has the lowest energy. Blue or purple, violet has the highest. And also it looks kind of like that. Okay, then we have ultraviolet radiation. So if you go out in the sun, you probably wear some sunblock or sunscreen that protects you from ultraviolet radiation. Ultra means beyond. And so here, we're going to have higher energy waves. And there's different kinds of UV radiation. Some are more harmful than others, and some are helpful, but only in small doses. That's how we get our vitamin D. Next on the spectrum are X-rays. And so again, they're going to have even shorter wavelengths. You can see my wavelengths are getting shorter and shorter as I go down the spectrum. These are harmful to human tissues. And so this guy's wearing a lead vest. Like if you've ever gone to the dentist office, they might put something over you while they take the picture of your teeth. Now, if you get, 1 or 2 X-rays a year, it's really not that bad. And that's why they're very quick pictures that they take. But if you were to get them a lot, that could be harmful. And X-rays cannot pass through lead. So if you've ever read or seen any Superman comic stories, Superman has X-ray vision, and one of his things is that he can't see through lead, and that's actually based on scientific facts. And it's used to take pictures of hard, dense tissues, and so that's why sometimes you get an ultrasound, sometimes you get a CAT scan, sometimes you get an X-ray. It's specifically to see teeth, bone, hard tissues like that, or they can look in, this is concrete, and maybe they look and they see if there's any cracks in the concrete, because that could be very bad if there's a crack in the foundation of like a building. And finally, gamma rays. So this is the shortest wavelength. Okay, so there's very, very short wavelengths, which is also the highest frequency and the most energy. Very dangerous, made by radioactive substances or nuclear reactions made in space. So, yeah, we don't really talk about those a whole lot, but they're like the most energetic. And so that